Okay, so as already mentioned, today we're going to talk about Numpy. This is one of the lectures from the Energy Data Science course. Of course, in that course, the lectures are accompanied by exercises and workflows and kind of live hands-on coding, which we won't be doing today. We're just walking through the lecture material here. So Numpy is probably the most fundamental package in what we call the Python data science ecosystem. Most of the other packages in that kind of ecosystem, that is the things that we use to do data science, data analysis, plotting, visualization, machine learning, all of those things. Most of the other packages in this Python ecosystem that you would use to do more advanced things build on top of Numpy or work interoperably with it. So it's really kind of the key, most fundamental package in the ecosystem. It's often said that Python is slow, and one of the reasons that it's slow is Python is an interpreted language, contrasted with a compiled language like C or C++ or many more. And that is that it's interpreted at runtime. So when you run the code, the system, the Python system basically looks at the code at runtime, determines what all the variables are, and then executes your code. When I say determine what all the variables are, that is, it sort of has to decide on the fly if a number is an integer or floating point number, because to do addition or do algebraic manipulations with integers and floating point numbers requires different instructions by the computer. And of course, even more different if it's you're doing some kind of string operations or something like that. Right? So in Python, we call, or this is often called duck typing, this runtime evaluation of the code. And that is, it's called duck typing or dynamic typing, because that is, if it looks like a duck, then it is a duck. In other words, in Python, if you have the number 1 without a decimal place, then the Python runtime transpiler is going to decide that's an integer and proceed until it runs into more information that, say you're trying to add an integer to a floating point number, then it'll convert that integer to a floating point number so that the operations can be done. And of course, all this happens at runtime. So that's what makes Python slow. Right? So this dynamic typing requires a lot of metadata around a variable. The solution to this is to use Numpy. So what Numpy offers are data structures as objects that have single type and contiguous storage. So that is, when we have a Numpy array, which we'll see examples of shortly, that Numpy array contains items of a single type. So a Numpy array will contain only integers or only floating point numbers or only complex numbers. And they'll be stored contiguously in memory. Contiguous means next to each other in memory. And there's some advantages of that when doing computations, just the way that the CPU accesses or caches from RAM. You get some additional speed up by having that contiguous storage. And then there's common functionality with implementation in C. So even though we use Numpy from Python, all of the actual numerical operations that are being done are done from a compiled library that's implemented in C, which is about as fast as you can get on a CPU. So if you carefully write Python code with using NumPy data structures, you can end up with code that's very much close to the same speed as you would get in compiled C, right? So just a couple examples. How slow is Python? We're going to use a time it module from the Jupyter project to time how long it takes to add 1 to a million numbers. So this is the Python code that would add 1 to the numbers 0, 1, 2, 3, 4, 5. So adding 1 to each of those and storing the result in an array. Okay. And I did this using a list comprehension in Python, which is much faster than a for loop would be, even itself. But nevertheless, if we do this, And this time it module, what it does is it actually runs this operation a number of times and reports some average statistics on it, right? So in this case, it takes on my computer 123 milliseconds to do this operation, to add 1 to a million numbers. And again, it's reporting statistics, so it did this over several times. Now in Numpy, not only is the syntax much easier, right? So the syntax that we're concerned with is right here. This first command creates an array of a million numbers, and then this +1 broadcasts that operation. I'll talk more about broadcasting later, but basically it broadcasts that operation across the array, right? So again, the first entry in the array is 0, 1, 2, 3, and each time I'm adding 1 to all those. So 0 + 1, 1 + 1, 2 + 1, and nice clean syntax to do that. But also, as you can see, it's about 100 times faster than doing it in pure Python. And this is a very simple operation. We can see even larger speedups when you have more complex operations. So another thing that Python gives us are these so-called universal functions or vectorized operations. So again, if we wanted to compute the sign of a million numbers, so the sign of 0, the sign of 1, the sign of 2, the sign of 3, all the way up, to a million numbers. To do that in Python, we'd have to again do that in a loop. I'm using the list comprehension. So again, this is the pure Python syntax here, just from the standard library. And if we do it, it takes 297 milliseconds. The Numpy operation, again, well, I guess not only am I computing the sign, but I'm squaring each number. So again, the syntax is much more compact. Here, what I initially create an array of a million numbers, and then I can call the sign function on the whole array. And it again, broadcasts that sign operation across the whole array element wise. So again, the sign of 0, the sign of 1, the sign of 2. It will do that. And then I square it on the end. Again, squaring the squared operation broadcasts across the whole array element wise. So it's this is the sign of 0 squared, the sign of 1 squared, the sign of 2 squared. And again, when you do it here, you see again like 100 times speed up using NumPy. There are many ways to create NumPy arrays. The simplest way is just to create them from a regular Python list. So if I have a regular Python list with the numbers 2, 3, and 11, I can just wrap them in this NumPy array. By the way, the kind of canonical way or idiomatic way that we always import NumPy is to do it with import NumPy as MP. The reason I take the time to point this out is that, when you go and you find help on Stack Overflow or elsewhere on the web, you're often going to see, this is the standard way that we import NumPy. So you'll always, when you see code with an MP dot something, you can just assume that that's NumPy code, that, NumPy functions that are being imported from the NumPy module. So again, returning to this idea of creating the arrays, we can create them from regular Python lists. And in this case, because all of the numbers in this list are integers, this constructor will by default assume that these numbers are integers and store them as such. Okay. We can also explicitly, so if I were to add individual decimal places after the numbers, that would specify that they're floating point numbers, and this would create, in this case, for example, this is going to create an array that goes from 1 to 4, and there'll be 6 entries in that array, right? So it'll include 1 and 4, and it'll have 4 additional entries that are evenly spaced, creating a linear space between 1 and 4. And because I use the decimal points there, this will explicitly be by default a 64-bit floating point number. We can also specify the type when we create it by specifying the data type, and you can look at the NumPy documentation to see all the data types. So there's 32 and 64-bit integers, 32 and 64-bit floating point numbers, complex numbers, strings, a lot of different types that you can use. Again, it'll automatically determine that this is a complex type upon creation because we specify it this way. And we can also like load in data from the file, and there's multiple options to do that as well. So these are just some ways you can create an array from data that you already have in Numpy. We're going to look at some other things you can do for what we call slicing or indexing or getting information from an array. So in this case, we're going to store the array. We're going to create an array that has 9 values that go from 0 to 8. The default will always start at 0 index if you use this kind of a range function. So, and then we're going to reshape that initially one-dimensional array so that the up to here creates a one-dimensional array. And then we're going to reshape that array into a two-dimensional array with this reshape function. So we have this two-dimensional array, or you might think of it as a matrix, right? Now in Numpy, we can actually have n-dimensional arrays. So there's no limit on the number of dimensions we can have. And I think I have an example coming up where at least there's 3 dimensions in the array. So we can get subsets of the array. This is called indexing into the array or slicing the array. We can get subsets of the array using this kind of notation. So the colon just implies all rows. So these are rows and columns. These the comma that separates these comma separates the dimensions, right? So this is the dimension that represents the rows, and the second dimension is the dimension that represents the columns. And again, if you add more dimensions, you just continue to add commas there. And so the colon is a shorthand syntax to say, I want all the rows, right? I want everything in this first dimension, which are the rows. And then the 0th column, right? So Python is a zero-based index language. So I want the 0 or the first column here. And you can see clearly that what is returned is 036. It's everything, all the rows in the first column. So there's also, these arrays are objects in the sense of an object-oriented programming language. So they have data or attributes associated with them. And in this case, you can query that data by querying the shape. So it tells you this is a 2-dimensional array with 3 in the first dimension and 3 in the second dimension. Some more kind of advanced slicing syntax here. What we can do is instead of an individual colon, which represents everything, we can also use start, stop, step notation. So again, this would be start, stop, step, right? So I'm going to go from the beginning. And so if you leave these blank, it's the same thing as saying I'm going from the 0th index to the length of x, right? So leaving them blank is just the default for that, right? Basically saying go from the beginning to the end. So start at the beginning, stop at the end, and go in steps of 2, right? So that's the syntax here. : 2, go from the beginning to the end in steps of 2. And you can see that that's what happens in both dimensions, right? So I start here, and I want to take the first all the way to the end, which is 2, and I want to do it in steps of 2, right? So I do that along the rows and the columns, and I have 0, 2, 6, and 8. And that's what's returned. In this case, I'm assigning the result of this subset or the slice to a variable y, and I'm printing out the variable y. And that'll be important in just a second. So when I demonstrate, okay, so now I can take, again, a subset of y, in this case, the 0, 0 index of y, this would be this first entry right here, and I can assign a new value to it. So in this case, I'm going to assign the value 100 to that first entry in the array, okay? And then I'm just printing out the results, and that's what you see here. Now, this next point I'm going to make is one of the most, it's a very subtle point that can trip people up when they're first learning to use Numpy, but it's very important for speed and efficiency to be able to do this. Now, what you notice is if we go back and we look at the array X, that was the original array we had, right? This original array we created here. we assigned the value y to this subset of the array x, and then we reassigned one of the values of y to 100. And you notice the original array x is also changed, right? So the original array x, the thing that is in the 0, 0 entry of that array, is also now 100, even though I made no operations, no assignment operations on any part of x. And the reason for that is that when I made this variable assignment y to this subset of x, what it did was it only created a view into the original array x, okay? It didn't create a copy or a new array. It created a view into the original array x. And so this is if you do this kind of thing, it's just something to be aware of. And, you know, of course, this is it's a feature, not a bug, because, you know, a lot of times all we want is a view or kind of shorthand views into the original data that we can make changes, and we want to change the original data. And of course, this also, there's some efficiency here because we're not making a copy of the original data, right? In this kind of small examples I'm using here, these copies would not be noticeable because it's just a 2x2 array. But if you had millions of data points in your array, then these copies can be very expensive. And so this is a feature, you know, to do this kind of thing. Now, if you explicitly want to prevent this, what you have to do is you have to explicitly say that you want to copy. So returning to the same syntax, I'm going to take you know, this 2x2 subset of the original array, assign it to a value y, but this time I put the copy on there. This makes a hard copy. And now if I change the first value of y to 200 and print the results, you can see that the value of y has changed, but not the value of x. It's still 100, which is what it was after we made the first change. Okay, so something to be aware of. You know, if there are any engineers in the audience, we often find ourselves in engineering solving some type of differential equations, or computing derivatives, and you know, a nice way to do that within Numpy is with this kind of efficient syntax you can use for computing finite differences. So I think what I'll do here is let's just look at a shorter example here of what's going on. So I have an array that I'm creating that goes from 0 to 40 in steps of 2. So we can just see that array there. So it's 0, 2, 4, 6, 8, right? And then the array y, I'm just squaring that array, right? So 0, 4, 16, 36, 64, right? So we know that an approximation to a derivative, a first derivative, is, you know, something like, in this case, using the variable names that I have here, it's like delta y over delta x. So I can compute delta y using this notation. First thing I'm going to do is say, all right, I'm going to use this slicing notation. I'm going to say I want the one entry of the y array. That's actually the second entry, right? So it's from 4 to the end, right? So if I say from 4 to the end, and if I print that out, you see that's what I get, right? From 4 to the end. Likewise, I can reverse this notation and put a -1 there. And so what this says is, this is the same thing as saying go from 0 to 1 from the end. And so if I run this, you'll see what I get there. And again, that's what happens. It goes from 0 to 1 from the end. So I can kind of combine these two to compute my delta y. So delta y is going to be equal to y 1 to the n minus, I'll print out the result. And so there we have, you know, this is the change in y. This is the delta y. And if we do the same thing for delta x, as I did in the second example here, and you see that we actually compute the dy dx, right? So this is an approximation to the derivative. And now I just have a plot here that shows I'm plotting those two results. So the first line is y of x squared right there. The red line, I'm sorry, the black line, clearly, right? It's a parabola. And then I can compute the derivative at the point 0 and plot the line. Then I have the slope of that line. And if you were to go and measure the slope of this line, you would see that it is in fact 2, which is the analytic derivative there. So just a nice way, this very compact way to compute finite differences from within NumPy. We can also, I gave a simple demonstration of broadcasting earlier in the sense that, we broadcasted the addition of 1 across an entire array. Likewise, in the finite difference example, we also did broadcasting. So broadcasting is a word for, broadcasting algebraic operations across dimensions of the array, right? So in the finite difference operation, we were subtracting 2 parts of the array for y and x, and then we divided them, right? So that division operation got broadcasted over all the entries in the array in an element-wise fashion. So in this case, just have a more sophisticated example for broadcasting. I'm going to start by creating 3 arrays of random numbers. Each of those will be basically 800 by 600. You can think of these as 2-dimensional images, or of like where each value represents a color, right? And that's why I call them red, blue, and green. And then with this, basically, I create these 3 arrays, right? So each of them have 800 by 600. So there's 3 arrays with those dimensions, and then I use those 3 arrays to create a new array that I'll call RGB. So ultimately my new array has a shape 3 dimensions, so red, blue, green, and then basically number of pixels in the x and y direction. And what I can do with this original array, RGB, is I can broadcast a multiplication operation over the entire array. So basically, if I wanted to multiply all red values by 1/2, all blue values by 1/2, and all green values by 0.25, I can transpose this array so that the 3 index becomes the last index. So then what I have is 600 by 800 by 3 after this transpose operation. And then I can broadcast this multiplication across all of those dimensions of the array, right? So basically, I just have to ensure that the inner dimension of this second, array matches the dimension of the outer dimension of the first array. So again, this first array after transpose is, well, maybe I'll just show it, right? So if it's originally 3, 800, 600, if I transpose the array and look at the shape, then I have 600, 800, 3. And then the shape of this is basically 3. So the dimensions will match, and I can do this multiplication across all dimensions of the array, and it happens basically instantaneously, right? So you can see if I execute this cell, just basically 1/2 times 800 times 600 operations just got done at the same time. 1/2 times 800 by 600 and 1/4 by 800 by 600. So that was a huge computation that was done really quickly, again, because the details are implemented in the C, right? So finally, we can just take a look at what is actually being done there. Is that you can think of this like scaling the color values in a picture, right? So this was my original picture, and then I scale it, and this is the resulting picture, and you can see the color differences right now. The pixels here were just random numbers, so they don't mean anything, but you can see the effect it has. NumPy, we also have this thing called fancy indexing, which can be really useful. So we're going to start over again with our original array of 9 entries, and we can index into the array just like we would index into a Python list, but with an integer value, right? So 3 would actually be the 4th value in the array, right? Because we start at 0, 0, 1, 2, 3, 0, 1, 2, 3. So the 3rd or the 4th value in the array, or the index 3 value in the array, is 3. And you can see that is returned, right? You can also, instead of just putting in an individual integer there, you can put in a list of integers, and it will return those. So in this case, the 1st, the 4th, and the last, the -1 means count from the end, the last entry in the array, and you can see that that's what we get again, 0, 3, and the last entry is 8, and that's what's returned, okay? So just want to point out the difference here. You cannot use fancy indexing with a regular Python list. So here I define a Python list and try to use some kind of fancy indexing, and I get an error. It will not work, right? But it does work for NumPy arrays. So just more examples here. Now I'm going to have a new array that I'm reshaping to be a two-dimensional array. So now I have two dimensions. I have to specify both dimensions, or if I want an individual value. Otherwise, it returns a row, right? So in this case, the 0th row, 0, 1, 2, right? Or the 1 and 2 index rows, which are the second and third rows, right? Again, by specifying a list. Or I can also specify entries like this. So the way this works, notice I have like a tuple of two arrays, and these are combined. So what I'm asking for here is the 0, 0 index, the 1, 1 index, and the 2, 0 index. And if you go back up here, you can confirm that that's what I got, right? The 0, 0 index is 0, the 1, 1 index is 4, and the 2, 0 index, that would be the 2 indexed row in the 0 index column, that is 6. And so there again, that's what I return. Right? So now we start to get into things that are a little bit more interesting and a little bit more towards, data analytics and, things that we would do with big arrays of data. So in this case, I'm just going to create an array of data that has 10 entries. And you see that because of random, some of them are positive and some of them are negative. What I can do is I can actually broadcast this greater than operation across the whole array, right? So basically, if I just say X, where X is greater than 0, what it will return is true where it's true, and you can verify this, right? 8 is greater than 0, 2 is greater than 0, and -6 is less than 0, so you get a false, right? And so what you end up with is this Boolean array, right? It's just an array of trues and falses that I can then use as a mask to mask back into my original array. So for example, if I only wanted values in the array that were greater than 0, positive values in the array, then I could use this kind of indexing. And by the way, you don't have to assign this Boolean array to a variable. I could, for example, switch this to basically just have this code right here, X greater than 0. And then you'll see. So because again, I reinitialized this, there's more negative values here. In fact, there's only two positive values in this array, 6 and 4. And you can see that is where this is true. Now I could also say greater than or equal to, and that will return the 0 values as well, right? So you can see how you can use these Boolean indexes as masks to basically select out parts of the data that you'd want from an array. Likewise, there's this kind of syntax, which is really just kind of an if-else type syntax. So I have this, basically this index is my Boolean array as stored here. And I can say, where this is true, return X, otherwise return 0, right? So in this case, where X is greater than 0, again, it's only 6 and 4. Everywhere else returns 0. So this is a way, you could start to do some kind of data cleaning. Say you had a quantity of interest that was recorded from an instrument and it had some noisy data, but the quantity of interest from a physical standpoint can't be negative. Perhaps some of the noise in the data causes that to be negative, and you'd want to zero out those entries for whatever reason. You could use some type of operation like this, right? So that kind of concludes the overview of NumPy, but I do want to mention some other closely related or extension packages to NumPy. The first being Xarray, and this is not going to be an exhaustive discussion of these. In fact, I just have one example of each. I'll refer you to their documentation if you'd like to see more, but these have some interesting extensions to NumPy. So NumPy is a very mature package. It's been around more than a decade. So these packages are both from the last few years, and they add some nice extensions to the NumPy package. And in the case of Xarray, it's using NumPy under the hood. So what Xarray is in a way to label the dimensions of your array, right? So we have n-dimensional data, and we have this indexing scheme, and for 1, 2, 3 dimensions, it's often not difficult to kind of understand or know like how to index into those. But if you have a very high dimensional data set, say it has 8 dimensions, your code is going to become very unreadable if you begin to index into an array that say had 8 dimensions, and you were indexing into it and something, imagine you had an array X that had 8 dimensions, then you had to index into it like something like this, right? Well, you would never be able to read this code because you don't know, what it would be very difficult to understand what, all of these different columns are or whatever. So with Xarray, it gives us a way to basically have labeled dimensions. So in this case, I start with a NumPy array. It has 10 columns and 3 rows, and I feed that data, assign that to a variable data. I feed that into a data array from Xarray, and then I label the dimensions. So in this case, I'm going to say the rows are just have the label index, and the columns have the label space, right? And then the coordinates of those columns for space anyway, I'm going to label X, Y, and Z. So the idea here is that I have 3 columns of data. This corresponds to dimension X. This corresponds to dimension Y. This corresponds to dimension Z. And you can see when it prints to the screen in a Jupyter notebook, you get some additional information about what's in there. But then the nice thing about this is if I want to say get all columns of the dimension space that are from the X column, then I can actually access just that column, right? So this is the first column of data here, just the first column. You can see the numbers there match up, 0.295, 0.70, right? So this is the first column of data, and I can access it via its label, right? So that's a little nice thing about Xarray. Likewise, you can do operations via their labels. So if I wanted to compute the sum across all rows, right? So I labeled this row dimension index. So what I'm saying is compute the sum down the rows of each column. And all I have to do then is call it like this. So my array X, I want to compute the sum across the dimension index, and that computes the sum of each column individually and returns the result there. So Xarray is just a way to basically have labeled n-dimensional data sets. Most of it is interoperable with NumPy or uses NumPy under the hood. So if you wanted to pass, say, one column of this data to a NumPy function, it would work that way. Okay. The next example is from JAX. So again, JAX is another package. Now, JAX doesn't use NumPy per se, but it replicates the NumPy API. In other words, you have these JAX arrays, and for the most part, you can use syntax that is in one-to-one correspondence with NumPy. But on top of that, you get GPU or TPU accelerated computations, as well as you get a compiler, so that these functions that you write in Python can be compiled to run on a GPU at near C speed. And you also get something called automatic differentiation. And that's what my example here is going to show, right? So imagine we have a function, f of x, that takes where x is a vector, right? So it has, x is a vector and it has 3 components, x0, x1, and x2. But this returns a scalar function, right? So if I feed in a vector that has 3 components, this returns a single value, right? Scalar. So if I want to compute the gradient of this function, and I pick some simple function that I can demonstrate, analytically what the math is, right? So if I want to compute the gradient of this function, the gradient is the derivative of the function with respect to each of the coordinates, right? So partial f x1, partial f x2, partial f x3. If I do that, and this is easy enough, I can do it analytically, right? I just compute the derivative of this function with respect to x0, that's 2x. the derivative of the function with respect to x1, that's 6x1, and the derivative of the function with respect to x2 is just 7. So this is the gradient of that function. And if I wanted to evaluate the gradient at a point, say 1, 1, 1, then I just plug in those values and I get this, 2, 6, 7. That's the answer, right? Well, we can do this automatically from JAX, right? So I have a couple of imports in here. The canonical way to import jax.numpy is with JNP. And then you can also import these functions like grad and Jacobian forward, which we'll talk about in just a second. But the first thing I'm going to do is define a function. So I'm using a lambda function to do that here, but you'll notice that this is just the function I wrote above, right? And this is a function of x. In the end, it's expected that x is a vector, and it's going to have 3 components, 0, 1, and 2. And so this is just the code that represents this function up here, right? Now, if I want to compute the gradient of f, all I have to do is, I imported this function grad. I just have to call grad on f, and that will give me a new function, which I'm calling grad f. And now I can evaluate grad f at a point. Let's say the point is 1, 1, 1. I call that function, and lo and behold, there I have the answer, right? So the JAX computed the derivative, in this case, computed the gradient rather. JAX computed the gradient for me. And then, when I evaluate it at a point, and I get the correct result, right? 2, 6, 7, you can see that there. Now, the nice thing about this is you can use this on compositions of functions. So you can have functions that call functions that call functions that call functions that are a function of x, and you can compute the gradient of x as part of all of that, chain of computations. And so an example of that here is basically I'm computing the cosine of the function that I computed earlier. Okay, so this is just my new function is the cosine of f of x. And then I compute the gradient of that, and then I compute the Jacobian of that, right? So if I have a scalar function, I compute its gradient, I get a vector. And if I have a vector and I compute its gradient, I get a tensor, right? And so that's what I have here. Now, this one I didn't go through the work of doing the math analytically, but if I evaluate that at 1, 1, 1, this is the result I get, right? So this is the what we would call the Jacobian of f, right? The gradient of the gradient of f, or the Hessian, you might call it the Hessian, the gradient of the gradient of f, right? And again, in this case, I'm not demonstrating that you can use GPUs, but you can see by default, it looks for a GPU. And on my laptop, there's not a GPU that can be computed on. So, it's saying no GPU found, falling back to CPU. You can turn this off if you wanted to by setting this variable, but this warning. But nevertheless, that's an example of how to use JAX. And if a GPU were found, it would automatically perform these computations on the GPU, and you would get an amazing speed up from that. Right? So with that, we're about the 45-minute mark here. I want to leave a few minutes for time for questions here. Are there any questions? From the audience? You can either raise your hand and I can call on you to ask the question out loud, or you can type it in the chat box. Okay, well, if there are no questions, then that will end this webinar, and I'll look forward to hopefully seeing you at another webinar in the future. Looks like I do have a question there. Does a gradient Jacobian work on a CPU with NVIDIA? I think you meant a GPU, right? So GPU, NVIDIA is a graphics processing unit company. They manufacture the graphics processing units along with the software framework CUDA for programming on those GPUs. And yes, the answer to that is yes. In fact, I'm not demonstrating just-in-time compile operation here, but if you were to also compile it in the presence of a GPU, what you would get is a gradient function that, basically the compiler will write the code for you and compile it to run on the GPU that will evaluate the Jacobian at a point. So it's blazingly fast if you do it that way. Thank you for the question. Yeah, so if there are no further questions, I'll look forward to seeing you all at another webinar, or possibly, if we piqued your interest, come take our energy data science class and to see more of what things like what we talked about today. Thank you, everyone.